I'm Blake, and this is Multidimensional Materials and Device Architectures for Future Hybrid Energy Storage. Through the review of literature, first one is the materials for electrochemical capacitors. This article has defined key research directions in the field of supercapacitors and pseudocapacitors, basically allowing us to understand the material properties that we want inside of these devices in order to make them as efficient as possible. The next article is Hybrid Energy Storage and Emerging of Battery and Supercapacitor Chemistries. This article has just reviewed through the current approaches to hybrid energy storage and combining capacitors or pseudocapacitors with batteries in order to make them extremely beneficial energy storage systems that can allow for our power-hungry needs in this day and age. Where do batteries end and supercapacitors begin? This is a description of the fundamental differences between batteries and double-layer capacitors and pseudocapacitors. Basically explains the fact that batteries are very high energy but low power, and that capacitors are very low power and high energy, where energy is the amount of voltage over time and the power is the amount of voltage total. So the capacitors end up displacing all of this high voltage all at once, while batteries have a lower voltage but displace it over a longer amount of time, giving it a higher energy. And the entirety of this article is combining them so we can get the best of both worlds. The next article is Anomalous Increase in Carbon Capacitance at Pore Size Less than 1 nanometer. This has stimulated research on supercapacitors and revitalized the field of electrical double-layer capacitors, because the double-layer capacitors that we are going to be talking about in this presentation is specifically carbon-based nanostructure double-layer capacitors, and we will get to them. The purpose of this article and slideshow is to explain the future energy storage, the options and effectiveness of these options, along with the drawbacks and limitations. The writers of this paper have not personally done the actual tests, but this is a culmination of 100 other articles that go into every one of the fine details that are about to be summarized in this presentation. Each of these articles are cited and go into specific details about combining capacitors with batteries, along with the use of different materials in the actual making of these, and electrolytes and the asymmetry of anodes and cathodes. These articles done their own testing, research, and simulations, and the conclusions that they have are being used in this presentation and in the article that this presentation is based off of. And some of these resources are just textbooks for material science and electrical engineering in order to understand the combination of these devices. There were no financial backings in this article, making it so then there are no active reasons for it to be biased or untrustworthy. And although it's a very well-informed article, it still understands that there are gaps in our current understanding of these kinds of devices, and that there is still further testing that is needed. So the first bit of data we have here, we have the electrical double-layer capacitor, the surface redox and intercalation pseudocapacitor, and batteries. Starting with the batteries, because they are the most simple, you can see that with 1V changes, which is the sweep rate, which ends up being the change in the amplitude, because energy works in sine waves, you can see that as the sweep rate increases, there's this peak here in the charge, but then in the discharge, there's the same peak, just that's reflected in the x and the y axis. And you can see that it's virtually the same along the next ones, but of course these two are virtually rectangular, so it's understandable that they are going to be symmetrical anyway. Uh, the intercalation suit. Actually, we'll move on to this. So with the potential sweep rate, it will hold for a longer amount of time with the same amount of sweep rate, and then go straight to zero, going from zero charge to full charge, which is basically the inverse of how the voltage to Q to Q max would end up being a starting high in voltage and then coming down and coming across and then down when you actually empty out the cell. And there is a phase change, which a phase change is just the physical change when going from charging to discharging and discharging to charging. And this battery uses intercalation, so inserting ions, and the change of oxidation states. So using redox reactions, which is just like iron turning into rust. That's a redox reaction. They're known for generally producing a lot of electricity, especially in lead acid batteries that we use today. Uh, so we will brush over the pseudocapacitors. Uh, of course, surface redox having a lot more rectangular shape than intercalation, and slowly getting closer to the actual electrical double layer capacitor. Both of them have no phase change, and this one has the same kind of operation of a battery, but it still acts like a capacitor. Uh, and just at the bottom, there's the example of the actual chemical, or not chemical, but the structural look of the actual batteries and pseudocapacitors. And then now for the actual electrical double layer capacitor, there is no oxidization state, so it is no matter what consistent going from sweep rate and current relations. And then you can see that because of that, you also get the linear, which this pseudocapacitor also has, because it also maintains a similar rectangular shape, just less consistent than this double layer capacitor. So this uses the high surface area carbon that I was talking about earlier, and it just picks up electrons and then discharges them as it pleases, kind of like a sponge. Now, the only challenge with all of this is you need to have access for these ions to move around. So, in this data, there is mainly we want to focus on this chart because this is just the same as these two are just similar to the last one, where it just shows the sort of rectangular state. This is one-dimensional, two-dimensional, and three-dimensional materials with specific capacitance in green, ionic conductivity in yellow, and BET surface area. So as you can see, with the three-dimensional material, you can see that the surface area is extremely increased, which also gives it just that bit of edge over split, so that it can have a higher specific capacitance, but also a lower ionic conductivity. And you can see how the more complex that these structures get, you also kind of get more and more actual functional use for specific capacitance. But when you use more advanced structures, you get less ionic conductivity. Now there's 0, 1, 2, and 3D materials, 0 being a clump, one-dimensional being tubes that can go in forward and backwards, two dimensions ending up having forward, backwards, but also having different layers, and three-dimensional having these complex shapes that can go forward, backwards, left, right, and up and down. So you can have this complex shape that will allow for a very efficient transfer of electrons and being able to properly function, to charge and discharge really quickly. And these just being real life electron microscope viewing of 1, 2, and 3D materials. So having asymmetric devices can allow for increased uh, energy, because when you just have activated carbon on these both, you only have a certain amount that you can actually use. But if you use like Me monoxide and activated carbon, you can have higher amounts of electrical potential energy to come out of your actual surface. And by making these uh, two electrodes asymmetrical, you can have this red line here, which gives you a lot more kind of freedom to do what you want, instead of having these symmetrical ones in blue, where you're kind of limited to here before you end up entering the oxidative decomposition of your electrolytes and the reductive decomposition of your electrolytes, which you don't want, because the electrolytes are what helps these electrical swaps go so well as they do. Now, these are your anodes and your cathodes. So there are multiple different ways that you do this. We are just going to cover A, B, and C. You can have the insertion materials, where you have two cations on both sides, where this one reduces into this one, giving you a positive actual cathode itself, or anode, sorry. And on this one, you can have it so that it reduces outside, making it so that this cathode ends up being negative to attract a positive charge. Then you can have this cathode that you can have this cation reduce to a rechargeable metal anode, making it so that you can carry a charge that way, or you can have a charge carrying ions that can change their oxidizing state without changing into a physical form, so then you can have it so then the cathodes and anodes themselves are just metal, while you actually have positive and negative cations and anions to actually utilize. Now, finally, the actual combination of all of this, putting battery supercapacitors and then using multi-electron chemistry, specifically using magnesium cations and sulfur anions for an organic redox reaction, and using sort of not acute, but a system where you have this clump of redox material, or not a clump, but this nano structure with these redox materials and electron pathways, so you can quickly charge and discharge while having that high energy density and power density. So using these pieces of information allow us to advance energy and power storage to a very advanced level, just by considering the use of super and pseudocapacitors with the batteries, using different materials like carbon nanotubes and different electrolytes, and altering device symmetry and utilizing multi-electron redox processes, just redox reactions that are more efficient, and we can have batteries that can last us for a long while. So the conclusion is the potential of hybrid energy storage is extreme in the amount of possibilities and combinations of these different aspects. But that's also kind of the bet withdraw, where you end up having issues in having so many combinations that you don't know which one will end up being the most effective. Thank you for seeing my presentation. I'm Blake. This was my presentation.